Paris to New York to London and Milan, you're probably wondering what all these places have in common. The one thing is runway. My name is Debbie Frost, and I'm here at the Edenvale University to speak to Professor Smith, which is behind these doors, to explain to us the macroscopic properties and the microscopic structures of what goes behind runway. Let's take a look.
Good morning, Miss Frost. I see you here for your interview.
Yes, Professor Smith. So, we all know runway is about the beauty, the fashion, the glitz and glamour, as well as the chic, but it all really comes down to one thing, materials. So, Professor Smith, what is a material?
Well, you see, Miss Frost, a material is the matter from which something can or is made. And to date, there are over 300,000 different types of materials that things can be made of. And material scientists, like myself, are discovering new ones every day. So the possibilities are literally limitless. So, come with me and take a look at some of the aspects of runway that you might not know.
Makeup. In runway, obviously all the models wear makeup. There are a variety of different looks, such as the cat eye, and you can have contrasts on your face, and there is a very plain and simple boring look. Obviously, in all of the models' makeups, the most essential part is their base. Doing this, she will be explaining the macroscopic properties and the microscopic structure. So, Professor, we all know the functions of base, but what is base really made out of?
Well, Miss Frost, base is made of a variety of different substances, such as water, pig's oil, and a substance called octyl methoxycinnamate. So, octyl methoxycinnamate is used in your base to protect your skin from the harmful effects of the sun's UV rays. In its liquid form, it is a clear and odorless substance and is insoluble in water, but soluble in both alcohol and oil, which is why pig's oil is used in your base. This is a model of the microscopic structure of octyl methoxycinnamate. The chemical formula for octyl methoxycinnamate is C18H26O3.
We all know about base now, but what about mascara?
Well, Miss Frost, mascara is made black by a substance called carbon black, and if you use brown mascara, it's made that color by iron oxide. The main ingredient in most mascaras is a substance called stearic acid. Now, stearic acid is generally found in the form of pressed flakes, which can be white or yellow tinged in color. They often have a solid waxy consistency. Stearic acid is soluble in alcohol, ethanol, menthol, and acetone, and the solubility of it is increased when the temperature is increased. And if heated, stearic acid becomes clear. This is the molecular structure of stearic acid. The chemical formula for stearic acid is C18H36O2.
Nowadays, it does not matter whether you are born with curly or straight hair. The new day technology can include things such as curlers, straighteners, and even crimpers. But how do all of these work, and how do they change the structure of your hair?
Hair irons work by breaking down the hydrogen bonds found in the hair's cortex. These bonds enable your hair to bend and be either curly or straight. Once broken, these bonds are only able to be reformed once your hair is exposed to moisture. Most hair irons contain a Teflon coating. Teflon is a white-grey substance that is found most commonly in its solid form. It is inadhesive, so therefore is most commonly used as a non-stick coating and is resistant against water and other organic compounds. This is a model of the molecular structure of Teflon. Teflon is otherwise known as polytetrafluoroethylene. Its chemical formula is C2F4.
As we all know, there are many different types of materials that clothing is made out of on runway, but the two most common is cotton and nylon. Nylon got its name from the two places it was founded, from New York and London, making it nylon.
Cotton fibers have a soft texture and are highly absorbent of liquids and retain their color well, but they burn readily as well. 91% of cotton is made up of cellulose. This is a model of the microscopic structure of cellulose. The chemical formula for cellulose is C6H10O5. Nylon fibers are highly resilient and resistant against organic factors such as bacteria and mildew. They are abrasion resistant and retain their color well once dyed. Nylon 6 has a higher tensile strength than any other fiber and can be permanently set by use of heat or steam. This is a model of the microscopic structure of nylon 6. This trampoline is also made out of nylon.
We all know that we cannot have runway in the dark, and it wouldn't be the same without all of the lighting. Some designers have even gone as far as to put lighting in their clothing. But the word I keep hearing is LEDs. So Professor, what are LEDs?
Well, Ms. Frost, LED stands for light emitting diode. LEDs generate voltage when exposed to light. They generate a different voltage according to their color. LEDs are highly economically efficient as they rarely ever burn out, are impact resistant, and draw very little power. LEDs all contain anodes and cathodes like every other diode. This is a model of the molecular structure of most common LEDs. The most common crystals used in the fabrication of LEDs are based on the mixtures of pure, group 3, and group 5 elements, such as gallium nitride, silicon carbide, zinc selenide, and a mixture of gallium, aluminium, arsenic, and phosphorus.
Part of the runway is the ramp. Most ramps are made out of stainless steel. The macroscopic properties of stainless steel is that it is hard, it does not rust, stain or corrode, it is impervious to water and air, it's recyclable, resistant to fire, and stainless steel items will not be damaged when washed. It is an inert material and it has good mechanical properties. Stainless steel does not have a microscopic structure as such. Stainless steel is made of iron, chromium, carbon, nickel, and small quantities of other metals. Stainless steel is a metal alloy and as such it does not have a chemical formula. It is a mixture of materials. Accessories make an outfit. But for some people this is very expensive and impractical. So Professor, what is the solution to this?
Well, most people choose to buy electroplated jewellery. Electroplating is when you use a current to plate a metal with another metal. The most common metal used for electroplating is silver. The macroscopic properties of silver are: silver is an excellent conductor of heat, electricity, and pure silver has the highest electrical and thermal conductivity of all metals. It is highly malleable and with excellent solderability and lubricity. A very ductile metal, which is why it is often bonded with other elements to form stronger alloys that still contain similar properties to that of silver and appear to be similar to silver. Silver is a soft white metal that is silver in color. Silver is considered a precious metal even though it has the ability to oxidize. The molecular structure of silver plating is Ag. The bonds between silver atoms is a metallic bond and the melting point of silver is 961.78 degrees Celsius and its boiling point is 2,162 degrees Celsius. That's pretty hot. Just like the jewellery.
Experiment silver plating with metal charm.
So what you need is silver nitrate, a glass beaker, silver rod
that has been cleaned,
a 9-volt battery with crocodile clips connected to the bolt.
You'll connect the negative port to your charm
and the positive port to your silver.
Like this. You'll pour enough silver nitrate just to cover a little bit of the silver
in your beaker.
You'll then place both the metals inside the solution.
as you can see, a reaction is occurring.
You can see the chain becoming almost different color. The water becomes really black and murky. Leaving this charm in the solution for a while, and after polishing it for quite a bit, all the black comes off, and you can see some parts being silver.
And once you've removed it from the solution, you can see the solution has changed colour from being clear to a murky brown colour, and a layer of coating has formed on the silver rod.
And that's how you use silver plate
Jewellery. We all know that if you look good but don't smell good, you really don't feel good.
So, in order to look good, you need to smell good. That is why today, for our experiment, we are making
A pineapple flavoured ester.
which is perfume.
So what you need is
10 ml of ethanol
50 ml of propanoic acid,
and 4 to 5 drops of sulfuric acid.
as well as an LMI flask,
A glass stirring rod,
a separating funnel,
2 beakers,
a measuring beaker.
and a trap filled with hot water.
In this beaker is 10 ml of ethanol and 50 ml of propanoic acid.
And in this pipette is the sulfuric acid that we are going to be dropping.
Okay. So be careful when you put it in to run it down the side so it doesn't only form a layer along the top, so it forms from top and bottom. Okay.
Now we're going to be adding the boiling water to this beaker,
And then swirling this around within it to heat up the liquid. Remember not to make it too full, or else when you put in your LMI flask, it's going to overflow.
as you can see, we are now stirring the liquid
Inside
as
the,
it's heating up inside the boiling water.
inside the LMI flask, you can actually see steam coming out.
As I'm stirring. This is not from the hot water, but it's coming from the actual
Liquids within the LMI flask. The acid may take quite a while to react, so if you're in a hurry or you're waiting for it for quite a while, you can always leave it to stand overnight and just put a cork on top of the LMI flask and leave it to stand in the warm water.
As you can see, we have left it overnight, and you can see an oily layer on top of the acid, that being the ester. We will now take a separated funnel and separate the two liquids.
As you can see, we are pouring this mixture into the separating funnel so your edges separate more easily.
So there is a proper funnel.
Really? Indeed we can. Now we leave it for a few moments for the ester to settle on top and acid to settle below. As you can see, we are using the separating funnel to separate the excess acid from the ester on top. Use a larger beaker to filter the acid into, and then once you get to the end of the acid, use a smaller beaker. Once you start seeing drops of oily liquid on top of the bigger beaker, stop. To finish separating the excess acid from the ester, use a smaller beaker to strain the rest of the ester into a small beaker so you can smell it and look at it and examine it properly. This is the ester that was left over after we've drained away the excess acid.
And now you should be able to smell the pineapple. Smells like pineapple.
Fruity, just how I like it.
Great.
Feel it in the air, yeah. She's a mean and crazy, dictator, disco.